So, have you ever actually stopped to wonder why sweating cools you down, or how a simple clinical thermometer knows exactly when to stop rising? Well, hello and welcome to this explainer. I'm absolutely thrilled you're here with us today because we're embarking on a genuinely fascinating journey through the world of thermal physics. We're going to zoom right in, starting from the everyday temperature readings you might see on your wall or check on your phone, and we're going to travel all the way down to the microscopic level. We want to witness the hidden energy that's literally breaking molecular bonds. This deep dive into physics dictates almost everything around us, from the weather patterns brewing outside your window right down to the massive steam turbines generating the electricity for your house. It's a spectacular ride that bridges the gap between what we can physically feel and the invisible forces that shape our entire world. Here is our roadmap for today's explainer. We'll start with detecting the invisible heat, move into how heat actually travels, and then contrast evaporation versus bulk boiling. After that, we'll uncover the hidden energy of latent heat before wrapping up with safety and accuracy first. Let's get right into it. Section 1. Detecting the invisible heat. Okay, let's dive into this. Heat is an incredibly powerful force, right? But it's fundamentally invisible to the naked eye. So the big question becomes, how do we actually capture and measure thermal energy accurately? To measure temperature, we have to rely on what's called a thermometric property. This is simply a physical trait of a substance that varies measurably and, most importantly, dependably whenever the temperature shifts. In those classic liquid and glass thermometers we all know, we're quite literally watching a fluid swell and push its way up a narrow glass tube as it absorbs heat. But modern science goes a lot further, using changes in electrical resistance or potential differences to track that heat. The key here is finding a physical property that acts as a perfect, predictable mirror to that invisible thermal energy. Now, when scientists are designing those classic liquid and glass thermometers, they face a really crucial choice of which liquid to use. Mercury, for instance, has a much wider range between its melting and boiling points. That allows it to survive and accurately measure brutal industrial extremes, even though it actually expands a bit less overall. Alcohol, on the other hand, expands quite well and is absolutely perfect for reading the temperature in your backyard on a freezing snowy day. So the specific physical properties of these liquids dictate exactly what kind of heat trucking tool we're building. So the crucial takeaway here is that in thermometer design, sensitivity and range are fiercely opposing characteristics. It's a classic engineering trade-off. You just can't have both. If you want a more sensitive thermometer, meaning one that gives you a large, easily visible rise for just a tiny 1-degree temperature change, you absolutely have to decrease the diameter of the tube bore. But if you want a wider range of temperatures, you have to do the exact opposite. Decrease the bulb volume and increase that tube diameter so the liquid doesn't just run out of space and burst the glass. And for better linearity, which just means the liquid thread rises uniformly across all temperatures, you need a liquid that expands perfectly uniformly. A brilliant real-world application of this tug-of-war is the clinical thermometer. Think about it. When you have a fever, a fraction of a degree matters deeply. Because human body temperature only fluctuates within a very narrow window, we gladly sacrifice the ability to measure a boiling pot of water with that thermometer just to achieve incredibly high sensitivity for monitoring our health. Section 2, how heat actually travels. All right, now that we know how to measure this invisible energy, let's explore how it actually gets from point A to point B. The first and probably most straightforward method is conduction. This is heat transfer through direct physical contact. Think of a crowded stadium doing the wave. Vibrating particles pass their kinetic energy directly to their immediate neighbors. This is exactly why leaving a metal spoon in a hot pot of soup quickly burns your hand. It's especially effective in really dense materials like metals, where all those particles are packed super tightly together. Next up, we have convection. This one applies exclusively to fluids, and in physics, that means both liquids and gases. When a fluid heats up, it expands, becomes less dense, and naturally rises to the top. As it moves away from that heat source, it cools down, becomes denser again, and sinks right back down. This continuous loop creates powerful circular convection currents. It's the exact same fundamental physics that drives the sea breezes you feel on the beach. The land and the ocean heat and cool at different rates, constantly feeding that massive circular weather loop. Finally, there's radiation. Unlike conduction and convection, radiation requires absolutely no medium to travel through. None. It transfers energy via electromagnetic waves, meaning it can easily cross the vast, empty vacuum of space. Think about that for a second. It's a mind-bending reality of physics that allows the sun to heat the Earth from 93 million miles away. And keep in mind, all objects, including you and me, are constantly radiating heat, and the hotter they are, the more they radiate. Surface color and texture play a huge role here too. Dark, matte surfaces are excellent at both absorbing and emitting radiation, while shiny, pale surfaces are great reflectors but terrible emitters. Why this matters is perfectly illustrated when we look at everyday house insulation, or even why we naturally choose to wear light-colored clothing to reflect the blazing summer heat. Section 3. Evaporation versus bulk boiling. Now, what's really interesting about this next concept is that people often use the words evaporation and boiling completely interchangeably. But in physics, they are vastly different phenomena. Let's heavily contrast these two. Evaporation is strictly a surface phenomenon. It happens when molecules at the very top of a liquid happen to gain just enough kinetic energy to break their intermolecular bonds and escape as a vapor. Because it only requires local energy right at the surface, evaporation happens at literally any temperature below the boiling point. It's exactly why we sweat to cool down, or why your wet clothes will eventually dry on a washing line even on a chilly day. Boiling, on the other hand, is a bulk phenomenon. It requires the entire liquid to reach a specific temperature, the boiling point, where vapor bubbles forcefully form throughout the entire volume of the liquid, not just the top, and rise to the surface. So what actually controls the rate of evaporation? Well, a higher temperature obviously increases the overall kinetic energy of the molecules, getting them moving faster. A larger surface area acts kind of like opening more doors in a crowded room. It just provides more escape routes for those surface molecules to leave. Lower atmospheric pressure also speeds it up because there is less external pushback from the air, keeping the molecules trapped in the liquid phase. And naturally, liquids with weaker intermolecular forces are going to evaporate much, much faster. These dynamics are tied to thermodynamic principles that subtly run our everyday environments, dictating everything from the humidity in the air we breathe to how massive industrial distillation plants manage to separate chemicals. Section 4. The hidden energy, latent heat. We're now going to shift our focus slightly to look at a phase change in action and try to calculate the scale of what physicists call hidden energy. Think of the bonds holding molecules together as tiny, tight little springs. When a substance undergoes a phase change, say melting from a solid to a liquid, or boiling from a liquid to a gas, something highly counterintuitive happens. The temperature completely stops rising. It just plateaus. Instead, all of the thermal energy being pumped into that system goes entirely into breaking those spring-like bonds. It frees the molecules from each other rather than raising their kinetic temperature. Because this heat doesn't actually register as a temperature change on a thermometer, it's famously known as latent or hidden heat. And we can actually brilliantly illustrate how to calculate that hidden energy using a simple formula. Energy equals specific latent heat multiplied by mass. The specific latent heat is the exact amount of energy required to change the state of 1 single kilogram of a substance. So, for example, if an experiment shows that it takes 99,500 joules of energy to turn 500 grams, which is exactly half a kilogram, of liquid nitrogen at a freezing negative 196 degrees Celsius into a gas, we can easily calculate its specific latent heat of vaporization. We just take that energy, divided by the half-kilogram mass, and we find that nitrogen requires a massive 199,000 joules per kilogram just to break those molecular bonds. To give you a truly tangible sense of the massive energy scale required to manipulate thermodynamics, consider the specific heat capacity of water. It sits at 4,200 joules per kilogram per degree Celsius. That means it takes 4,200 joules of energy just to raise the temperature of 1 kilogram of water by a single solitary degree. Water's incredibly high capacity to absorb heat is exactly why it takes so much energy and time to heat up a pot of pasta water on your stove. On a planetary scale, this means our oceans act as giant global thermal batteries, soaking up the sun's heat and preventing the Earth from freezing over at night or boiling during the day. It's an absolutely crucial mechanism for life. Section 5. Safety and accuracy first. As we pull all of this incredible theory together, we absolutely have to talk about how we handle these extreme thermal forces safely in a real laboratory, because theoretical physics relies entirely on rigorous physical safety and precision. During thermodynamic experiments, it is essential to wear gloves when handling hot objects, like heated water containers. If you're using electrical heating circuits, every single connection must be checked and approved before switching the power on to avoid dangerous shocks. If you happen to be using a mercury thermometer, any spills require extreme care and specialized cleanup due to toxicity. And for accuracy, well, you must avoid parallax errors. That means you cannot look at a thermometer from a weird angle. You have to view the reading at perfectly straight-on eye level to get the true measurement. Finally, to ensure your complex energy calculations are actually correct, you have to use lids and add insulation to your equipment. Otherwise, that vital thermal energy simply escapes right into the room and your data is ruined. We have covered a tremendous amount of ground today, zooming from the tiny bore diameter of a clinical thermometer all the way up to the massive, invisible energy required to break molecular bonds on a global scale. The next time you feel a sea breeze rolling in, or watch water evaporate off a hot sidewalk, or simply check the temperature on your porch, I want you to remember the intricate, beautiful dance of kinetic energy and molecular forces happening right in front of you. From the cooling systems keeping your car engine from melting to the massive steam turbines powering your city, I leave you with this question to ponder. Where else is thermal physics quietly running your world? Thank you so much for joining me in this explainer. Keep observing, and as always, keep questioning.